show our implementation of MPLS traffic engineering and MPLS VPNs in the software defined. So if you're familiar with MPLS, you all know that traffic engineering and VPNs are the two most important services offered by MPLS networks. But carriers find those services difficult to scale and manage. Why? Because of the complex MPLS data. So here's the typical MPLS network. Way too many protocols on one cloud. All these protocols are tightly coupled with the data plane, and each router you have a lot of state and a lot of processing. So very difficult to scale. Very difficult to introduce new services as well, because the new service requires to modify these protocols or introduce a whole new protocol. So, what if we take MPLS data plane, but we replace all of these protocols on OpenFlow application running on top of an infrastructure? It's meaning that you can provide the same services, but without the complexity. So let me show you. So here in this GUI, you see the real-time state of an emulated wide area network. We're using software switches here that support OpenFlow. So I have traffic jams running all around the network, and if you actually route them to IP, everything is going to take shortest path, and you'll probably have congestion along one link or the other. So let me go ahead and create a few OSPs for you to see how it's going. So the first OSP is from San Francisco to New York. The path of the OSP is from San Francisco to Denver to New York, and you can see it on the GUI as well. The reservation of the LSP is 123 megabits per second. The priority is 0, which is the highest, and the usage is 11 megabits per second. And it has auto bandwidth and is carrying VoIP and video traffic. So the next LSP is going to be from San Francisco to Houston. This one is going to be having different reservations, different usage, and different contracts. So if you look at these two LSPs, you realize that they actually take the shortest path. Why? Because there's enough bandwidth available for the reservation. But if I click the new LSP from San Francisco to Kansas, that one is going to take a longer path. Why? Because there is not enough bandwidth along this link. We allow a maximum of 900 megabits per second to be reserved. If you look here, you see there is already 823 megabits per second reserved. And this is just too much traffic to go through the same infrastructure. Now, our fourth LSP, this one is going to be from New York to Houston. This one is going to have auto bandwidth on. So the reservation of 10 megabits per second, usage is a lot more, but because of auto bandwidth, the reservation is going to catch up to the usage. So let me go ahead and click our next LSP. This one is going to be from New York to Phoenix. And if you actually look at the reserve capacity on this link, you just saw that it went up to too much, and then now you have to do that. So what actually happened was that our auto bandwidth kicked in, updated the reserve bandwidth, and then you were overusing this link. So what we had to do, we had to reroute the lowest priority LSP. So this was our TE demo. Let's get back to the code. So what I just showed you was implementation of MPLS traffic engineering and software-defined network. The features were implemented with mission control, traffic-aware LSPs, auto route, auto bandwidth.
I will start OpenFlow in my office.
It took 2 hours, 3 months, and under 4,000 lines of code. Probably half of the code went into So I just showed you pretty much everything, every major feature for traffic engineering. Now let's head to VPNs.
Packaging a complete solution.
So these two GUIs show two views of the same network. So this is also a wide area network that's emulated using software switches. But the difference here is that here you have two different customers. If you look closer, you have McDonald's and Sears. They each have 4 offices, and the IP addresses in those offices are overlapping. So what we do in this demo is actually show you how easy it is to create VPNs using our approach. So let me go ahead and do this. So very simple, click on create a VPN, and you see the customer's address, click here, and then you use the topology. So for this one, let's go with full mesh, and then you click on launch, and then close up. So on the right hand side, you see the actual paths of see the virtual links those LSPs represent. So if you look at the left GUI, you see actually a full mesh topology happening. So creating a VPN for McDonald's is as simple. So again, you click on create a VPN, you select customer edge router, and then we choose our topology. Let's use hub and spoke for this one. And we click OK, and then we launch. And we wait for a couple of seconds. There we have our VPN. So if you look on the left-hand side, you actually see a hub and spoke topology happening in the left-hand side. And in the right-hand side, you see the So let's get back to the post. So what I just showed you was an implementation of MPLS VPNs in a software-defined network. All of the LSPs you just saw were MPLS TV LSPs. So they come with all the features I showed you in the previous step. And so we handle overlapping IP addresses and we give the user choice of topology. And we saw how user-friendly it was and how simple it is. And this work took just 3 months with under 1,000 lines of code to implement. So to wrap things up, we just showed you our implementation of MPLS services in a software-defined network. But this was just a full implementation. But the fact is that you can see the potentials of our work. You can see that we can optimize our services globally, we can make our services more dynamic, and we can easily introduce new functionality. That functionality is just an application sitting on top of the control. All that was done from MPLS with a control plane that's based on a software-defined network.
Awesome.